And this just shows that there's a correlation between the axial elongation and the change in refraction, which is reassuring, but other than that, it's not really of particular interest. It just, we think this shows that we know what we're doing. When we reduce the axial elongation, we do actually reduce the refractive error change, which is encouraging. Okay, so the first study I want to talk about controlling these, about combining these methods, is to say, well, if multifocal optics slow myopia progression and orthokeratology slows myopia progression, could we combine the two into a multifocal orthokeratology? In other words, the aim of this study was to slow eye elongation more effectively than conventional orthokeratology by molding a multifocal surface onto the cornea. So up there we've got, on the right-hand side, we've got this weird, I'm sorry, my drawing's not that great, but what it's supposed to show is that we're molding a multifocal surface onto the cornea. The children wear these lenses overnight, and when they wake up, they have this complex multifocal surface molded onto the front of their cornea as if they were wearing a multifocal soft contact lens. Okay, so the study design, it was prospective, randomized, and it was a paired eye study, paired eye comparison study. So one eye, so I'll get to that in a minute. The investigators were masked to which eye the child was wearing the experimental lens in. We had 30 children, they were aged 10 to 14 years. Their myopia progressed by at least 0.5 diopters in the previous year before they entered the study. They had spherical refraction of relatively low myopia. And for 18 months, every night, they wore the novel multifocal lens in one eye and a conventional orthokeratology lens in the fellow eye. So we aimed to compare the progression in the two eyes of each individual because we expected to see a change in a more effective inhibition in the eye wearing the multifocal lens. Now this paired eye study protocol has many advantages, but I don't really have time to talk about them, so I'll just talk about the actual results. Sorry, okay. So, of course, orthokeratology gets rid of the refractive error, so in fact we measured our efficacy by measuring the change in axial length. And we used a thing called a lens star, which is an optical low coherence reflectometer, and it can measure all sorts of things. It can even measure the thickness of the choroid, it can measure the vitreous chamber depth, it can measure the axial length of the eye, which is from the corneal apex to the retinal pigment epithelium, and it can actually measure the inner axial length as well. So what happened? Right, the green line here shows the change in axial length over 18 months in the eyes wearing conventional orthokeratology. There are 30 children in that group, or 30 eyes in that group, sorry, and you can see that there's still a certain amount of progression, but it's not very significant because that dotted line that I've put in there is remember these were children, their eyes were still growing, and actually that's the rate at which you'd expected their eyes to have grown, their axial elongation to have grown, if they were emmetropic children. So conventional orthokeratology has almost abolished the axial elongation. But more interestingly, the eyes that wore the multifocal lens, actually after the first couple of days, their eyes had actually got shorter. And then you can see the line dips down to minus whatever it is, 0.1, and then gradually increases back to its original length, which we found quite unexpected. Now remember, down the bottom here we're measuring axial length, which is from the corneal apex to the retinal pigment epithelium. So we started to explore what was happening in a little bit more detail, and if we looked at the vitreous chamber depth, we saw the same effect. We saw elongation in the eyes wearing conventional orthokeratology and a shortening and then slightly elongation in the eyes wearing multifocal orthokeratology lens. And it wasn't until we actually looked at the thickness of the choroid that we realized that this was all explained by the fact, or not all explained, but partially explained by the fact that the choroid actually got thicker in the lens, in the eyes wearing the multifocal orthokeratology lens, whereas it got thinner in the eyes wearing conventional orthokeratology lenses. Now, you can see from this diagram down the bottom here that C represents the choroid. If the choroid gets thicker, it pushes the retinal pigment epithelium forward and the vitreous chamber depth gets less, and so does the axial length. So the explanation for that change in axial length is probably changes in the choroid, but that, as I say, was quite unexpected. Okay, so the conclusion of the first study was both MiSight contact lenses and ortho-K slow myopia progression in children about equally, between about 45 and 50%. Dual focus soft contact lenses are initially quicker and less expensive than ortho-K. Ortho-K has particular advantages, however, because children like the idea that they don't have to wear any lenses during the day because they have their unaided vision is 6/6 without wearing anything. So that's a big plus for practitioners who use ortho-K. It's very attractive. But there is a potential to improve the efficacy of conventional ortho-K by using multifocal ortho-K. So potentially we can combine two methods to improve efficacy. Okay, so that's the result of the first study. We then did a little study looking at the business of optical defocus and choroidal thickness. And what this slide shows here is that if we put this dotted red line here is the image plane, and this is in humans, in young humans, and this is an OCT image of the retina and choroid. If we put the image plane anterior to the retina, then what happens over a course of 60 minutes is that the choroid gets thicker by about 20 microns. If we keep the image plane actually at the photoreceptors, then the thickness of the choroid doesn't change over the same period of time. If we put the image plane to the posterior to the retina, in other words, we create hyperopic defocus, then what happens is that the choroid gets thinner. Now, this information is going to be part of the necessary understanding for the next part of the next study. So now I want to talk about the second study, which is combining atropine with optical defocus. And in Taiwan, where this study was done, 50% of children with myopia are prescribed atropine of a variety of different concentrations. Very low-dose atropine is regarded as slowing myopia progression by about 50% over quite a long period of time. That study was over 5 years. But the site and the mode of action of atropine in slowing progression is not clear. And atropine causes thickening of the ocular choroid in animals and in humans. This gives you an idea of what we're starting with if we just talk about atropine. Atropine slows myopia progression depending on the concentration by something like over 70% to something like 50-something%, depending upon the concentration. So it's actually about the same, has about the same efficacy as orthokeratology and multifocal contact lenses. So I'm going to finish by talking about the second study, combining atropine and optical defocus. So the aim was to investigate whether efficacy of myopia control is likely to be enhanced by combining optical and pharmaceutical methods into a dual therapy. It's been proposed that the choroid acts as an intermediary in the eye growth signaling pathway from the retina to the sclera. It sits between the retina and the sclera, and there's a lot of evidence that the choroid actually is involved in eye growth control. Moreover, as I said earlier, these studies in animals show that before the eyes elongate or shorten, the choroid